Inequalities involving quadratic functions. So chapter 3, section 5. So up to this point, we've dealt with quadratic equations and we've solved them. And we realized that quadratic equations just represent parabolas. So now we're going to deal with quadratic inequalities. So if we're going to solve a quadratic inequality, such as ax squared plus bx plus c greater than 0, where of course a cannot be equal to 0 because otherwise it's not a quadratic equation, then the first thing we're going to do is we're going to graph that quadratic function. So we set f of x equal to ax squared plus bx plus c, and we graph it. Once we graph it, we can determine where f of x is greater than 0, and we have solved the inequality. Now, if the inequality is not strict, meaning it's not just greater than, but it's greater than or equal to, then we would also include the x-intercepts. So let's try an example. If we have 5x squared plus 3x minus 2 greater than 0, we want to find for which values of x will this inequality be true. The first thing we're going to do is we're going to set it as a function. So f of x is equal to 5x squared plus 3x minus 2. And then we're going to graph that. I use Desmos.com, so you can see that it's graphed here. And I clicked on the two x-intercepts, and I found them to be at -1, 0 and 0.40. So for f of x equal to 0, x is equal to -1 and 0.4. Now that I look at this, I can see, first of all, I see that it is a strict inequality. Right? So y cannot be equal to 0. It's greater than 0. We're not looking for when it's greater than or equal to 0. So it's a strict inequality. And I'm looking for a greater than, so I look at this and I see, aha. So when is this graph greater than 0? Well, starting at -infinity, going to -1, exclusive, and then from 0.4 exclusive to positive infinity. Remember, I can't include when x is equal to -1 or when x is equal to 0.4 because it's a strict inequality. We're looking for when the function is greater than 0. Well, what happens if we do the opposite? If we're trying to solve an inequality where ax squared plus bx plus c is less than 0, a obviously not equal to 0. We do the exact same thing. Graph the function f of x is equal to ax squared plus bx plus c. Determine where that function is less than 0. If it's not a strict inequality, then we'll include the x-intercepts in the solution. So we have 4x squared minus 7x plus 3 less than or equal to 0. So the function f of x is equal to 4x squared minus 7x plus 3. So I graph it again. I use Desmos.com. And we see that it crosses the x-axis at 0.75, 0, and 1, 0. It's not a strict inequality. It's less than or equal to 0, so y can be equal to 0, so we're going to include those points. And we're looking for where it's less than. Be careful, because this is where people tend to make the mistake, is they get in the habit of looking for greater than, and so they just automatically give the result as if it were greater than. We're looking for less than or equal to, so it's less than from 0.75 to 1. And since it's not a strict inequality, we'll include those x-intercepts. So we have from 0.75 inclusive to 1 inclusive. Well, yeah, sometimes we have something a little different. What if our inequalities are written in a different format? Instead of ax squared plus bx plus c greater than 0 or less than 0, sometimes it's written in a different format. So maybe we have ax squared less than bx plus c. Well, that's okay because all we need to do is rearrange the inequality so that 0 is on one side. So we just take that ax squared less than bx plus c and get everything onto one side so that it's an inequality with 0 on one side. Now with this, just remember when you multiply or divide by a negative value, that changes the direction of the inequality. But if you add or subtract a negative value, it does not change the direction of the inequality. Once we've rearranged the inequality, then we move forward and solve just like we did for our previous examples. So if I have 4 minus 3x squared greater than 5x, I'm going to start manipulating this. And the first thing I'm going to do is I'm going to just change the order on the left-hand side. So I'm going to call it negative 3x squared plus 4 greater than 5x. Then I want to get that 5x onto the same side as the rest of it. So I'm going to subtract 5x from both sides, and I get negative 3x squared minus 5x plus 4 is greater than 0. Now that I have my inequality, I can take the function f of x equal to negative 3x squared minus 5x plus 4, and I can graph it. And when I do, I get this. I see that it crosses the x-axis at negative 2.257, and it's 0.591. And I do notice also that is a strict inequality, so I cannot allow y to be equal to 0. Therefore, I'm looking for when it's greater than, so that is in the interval from negative 2.257 exclusive to 0.591 exclusive. And that's really all there is to solving quadratic inequalities. Turn it into a quadratic with a 0 on one side of the inequality, graph that quadratic function, look and see where it crosses the x-axis, so where it is a greater than 0 or less than 0, depending on what it's looking for. And then also take note of, is it a strict inequality or not? If it's a strict inequality, then we'll use parentheses. If it's not a strict inequality, then we will use the square brackets. And we come up with our interval or intervals. Now, one thing to take note of is there are not always x-intercepts. If the graph opens down and the vertex is below the x-axis, then there is no x-intercept there. And so it depends on what the question is. If it opens down and the vertex is below the x-axis, and we're asking when is it greater than 0, the answer is never. If we're asking when is it less than 0, all real numbers. So just keep that in mind and realize there doesn't necessarily have to be an x-intercept. There doesn't have to be an interval other than all real numbers or the empty set. So it could happen, we could have the result being all real numbers. We could have the result being a single interval. We could have the result being 2 intervals combined, or we could have the result be the empty set. Absolutely nothing.